this video, we'll introduce graph optimization, which is probably the largest and really most important idea in our module on graphs. The common thread that will connect all of the problems in this section will be the desire to optimize, so either maximize or minimize, some quantity associated with a graph. We will concentrate most of our attention on two of the problems, the traveling salesman problem, which we mentioned in our last lecture on Eulerian paths, and the maximum flow problem. Then at the close of this section, we'll briefly discuss some other types of problems. So first we need the definition of a weighted graph. A weighted graph, remember we usually denote a graph with a vertex set V and an ordered pair, a vertex set V and an edge set E. Now we also have a weight function, small w. So a weighted graph will have a vertex set V, an edge set E, and a weight function. The weight function will be from the edge set to the real numbers. If E is an edge in the edge set, then W of E will be the weight assigned to that edge. So you'll see in the examples coming up that the weight function is often a cost associated with an edge E, maybe something like a toll on a road or some other thing. So therefore, most of the weights will be positive. So here's an example, a distance graph. We'll take capital V to be the set of 6 capital cities in New England: Boston, Augusta, Hartford, Providence, Concord, and Montpelier. And then we're going to let E, and I think this should be parentheses here, so we're going to let E be the set of ordered pairs, AB, from the Cartesian product of V cross V, where A is not equal to B. So since we're taking E to be every possible ordered pair that's not where A and B are not equal, then this is going to form a complete graph. An example of a weight function on such a graph would be that W of, say, C1 comma C2 is just the distance in miles from city C1 to city C2. So many road maps have such a setup, and they define distance functions. So we could define a function from this table. So the way we would read this table is if we select a certain number, because that's at the intersection of Boston, Massachusetts, and Concord, then this is the distance from Boston to Concord. So that is an example of a weight function. Then the traveling salesman problem comes from this very idea. Given a weighted graph, like perhaps the road map of the capitals in New England, if we want to find a circuit that visits every vertex at least once and minimizes the sum of the weights, then any such circuit is going to be called an optimal path. So you notice that it doesn't say that we can't travel to the same city more than once, but it does say that our goal is to minimize probably the distance or the cost of the travel, something like that. So it's often not going to be optimal in order to revisit cities. So an alternative form of this problem would require that the circuit be Hamiltonian, but in this case we're not, but you might see that in some other textbook or some other application. In many applications, the graph in question would be a complete graph. If the weight on each edge is constant, then an optimal path would be any Hamiltonian circuit. So if the weight on each edge is the same, then finding an optimal path is the same problem as just finding a Hamiltonian circuit, which we talked about in the previous lecture is not always reasonable or possible. Okay, so going back to our cities in New England, the traveling salesman problem would get this name from the situation of a salesman who wants to minimize the number of miles that he travels to visit his customers. For example, if a salesman from Boston must visit all the capital cities of New England, then the problem would be to find a circuit in the weighted graph, which we'll see shortly. Note that the distance and the cost are closely related in this case, but additional costs might include, as I mentioned, toll roads or traffic congestion and other things that we could take into account. The search for an efficient algorithm that solves this traveling salesman problem has occupied researchers for years, and the problem is still not totally solved. If the graph in question is complete, then there would be n-1 factorial different circuits. So as n gets large, it's not reasonably possible to check every circuit. So the most efficient algorithm known currently for solving the traveling salesman problem has taken time proportional to 2 to the n times n. So an exponential amount of time. And since this quantity grows quickly as n gets large, we can't expect to have the time to solve the traveling salesman problem for large n. So most algorithms that have been developed will just find a circuit that is close to the optimal one. And one such algorithm is called the closest neighbor algorithm. So we're going to learn this algorithm. This is relatively simple and it doesn't always yield the best result, but it's an easy to understand algorithm. The general idea is starting at any vertex to visit the closest neighbor to the starting point. So, and the next vertex will be one that hasn't already been visited. So this is a short-sighted approach because the quantity is associated with only that step. It's not taking into account future choices. So here is the closest neighbor algorithm written out. But again, it's quite simple. The idea is just at each step in the phase, you're just going to pick your closest choice or your least costly next choice. So we'll see an example of this. So let's say we wanted to start at the vertex 1 and find the closest neighbor circuit. So starting at the vertex 1, I would choose to go to vertex 3 because 5 is less than 6. And then from vertex 3, my choices would be either to go to 2 or to go to 4. So I'd choose to go to 2. And then at 2, I can only go to 4 because we've already visited 1 and 3. And then from 4, I can go back to 1. So I needed to visit all of the vertices at least once. I needed to end up back at 1. So if I started at 1 and used the closest neighbor algorithm, the cost would be 5 plus 6, 11, plus 10, 22, plus 8 is 29. So following this path that we did, 1, 3, 2, 4, 1, the cost is 29. However, the optimal path, starting at 1, should be to go first to 2, which is not the choice that we made because it was more expensive and the closest neighbor algorithm is short-sighted. It can't see what's up ahead. But then, by doing this, this allows us to take this path next, which is cheaper than going to vertex 4. And then from 3 we go to 4, and from 4 we go to 1. So eventually it's 6 plus 6 is 12, plus 7, 19, plus 8, 27 is the cost. And this is the optimal path, or the optimal circuit, starting at 1. But the closest neighbor algorithm could not find it. Okay, so that was just a simple example. Although the closest neighbor circuit is often not the optimal circuit, we might be satisfied if it's close to optimal. So how would we determine if it's close to optimal? So if we know the optimal cost, then we can call it C sub opt. And we're going to call closest neighbor C sub Cn. So if these are the costs of optimal and closest neighbor circuits in a graph, then it's always the case that the optimal path is going to be less than or equal to the expense of the closest neighbor path. And so if we divide by the optimal path on both sides, we would have that the ratio of the closest neighbor, the cost of the closest neighbor path over the cost of the optimal path should be always greater than or equal to 1. If they were equal to each other, if C sub Cn and C sub OPT were equal, then this would be equal to 1. So we can assess how good the closest neighbor algorithm is by determining how small that quantity gets. If the quantity is always near 1, which is the smallest that it can get, then the algorithm is good. However, there are graphs for which it is large, then the algorithm can be discarded. So in this example, they're pretty close, right? We said that it was 29 for the path that we found using the algorithm, and it was 27 was the cost for the optimal path. So that's fairly close. 7% increase in cost may or may not be considered significant. Okay, let's look at another example. A salesman must make stops at vertices A, B, and C, which are all on the same one-way street. So the graph, which I'm going to switch to in just a second, is weighted by the function W, and that's equal to the time that it takes to drive from vertex I to vertex J. So this is our graph, and you can see we have one-way streets, because when we start, we can go towards C, towards B, towards A, and back around. So we have one-way streets because it's a directed graph. Now notice that if J is down the street from I, then the weight from I to J should be less than the weight from J to I. So what that's saying is if I'm here and my thing is down the street, say B, then it's going to be shorter to go from C to B than it would be to go back around to B. Okay, so that's what we mean there by being down the street. Oops. Okay. The values for the optimal and closest neighbor circuits are 20 and 32 respectively. Then it asks us to verify that the closest neighbor cost is 32. So we can do that quickly. We can see that I have to start at start. So it costs me 2 to get to C. Then I only have one choice. It costs me 10 to get to B. It costs me 10 to get to A. And it costs me, whoops, this one, 10 to get back to C. So that's 32, 10, 10, 10, and 2. Whereas the optimal path would be actually to start and go to A. We didn't make that choice with the closest neighbor path because 10 is larger than 2, but by paying this 10 up front, that allows us to get 10 plus 4 is 14, 14 plus 4 is 18, 18 plus 2 is 20. So because of the nature of this graph, the value of the ratio of the closest neighbor divided by the optimal is 1.6, which is much more significant. The salesman would spend 60% more to go from start to C to B to A than he would to go from start to A to B to C and back. Okay, so a more general result relating the closest neighbor algorithm presumes that the graph in question is complete. And remember, that means we have edges connecting all of our distinct vertices, and that the weight function satisfies the conditions. So this first condition, the weight from X to Y is equal to the weight from Y to X. This is called a symmetric condition. And then the weight from X to Y plus the weight from Y to Z should be greater than or equal to the weight from X to Z. This is called the triangle inequality. If you haven't seen the triangle inequality before, it's just saying that something like this plus this should be longer than the straight across path, right? We know that. The straightest path from point A to point B should be, rather the shortest path should be the straight path. So that's all the triangle inequality says, and that's the second condition there. So this theorem that we're about to present is assuming that these two things are true. It says if VEW is a complete weighted graph that satisfies the symmetry and triangle inequality conditions that we just discussed, then this ratio of the closest neighbor cost divided by the optimal cost should be less than or equal to, this means the ceiling function. In previous video, we've seen the floor function, so ceiling function is denoted like this. Floor function is this one. So the ceiling of log base 2 of 2n divided by 2. Okay, so ceiling function means that we just round up to the closest integer. It doesn't matter, not to the closest, but we go to the next one up always. So it doesn't matter if we're closer to the one below or the one above, we round up. So this estimation for a complete weighted graph will always satisfy this inequality. So then they've made the observation here that if the cardinality of the vertex set is 8, then the theorem says that this ratio can be no larger than twice the size of the optimal path. And that's just simply because if we plugged in 8 here, 2 times 8 is 16. Log base 2 of 16 is 4. 4 divided by 2 is 2. So just a simple observation that for a graph of 8 vertices, the theorem tells us that this estimation can be no worse than twice. The ratio can be no larger than twice. So this is what's called an upper bound. The ceiling of log base 2 of 2n divided by 2 is an upper bound for the ratio of the cost of the closest neighbor algorithm divided by the cost of the optimum. It tells us only that things can't get worse than the upper bound. We can be smaller than the upper bound. It just tells us that it can't be any larger. So certainly there are many graphs with 8 vertices such that the optimal and closest neighbor circuits are the same. We could try to draw one, and if you want to pause the video and try to draw one, I can assure you, you should be able to. So what is left unstated in the theorem is whether there are graphs for which the quantities are equal. So whether there are graphs for which this ratio is equal to this log. If there are such graphs, then we would say that the upper bound is sharp. That's the terminology we would use. So the value, you might notice, in one of the previous examples that we did was larger than this upper bound. Why is that true? Because the graph that we did that on didn't satisfy the conditions of symmetry and triangle inequality. So this will only apply under those certain conditions. Okay, so here on the top of the screen is what is called Dijkstra's algorithm for finding an optimal path. And I'm not going to go through it in detail with you, but we'll do some exercises later where we will use this algorithm. And it's similar in notion to our closest neighbor algorithm, although maybe a little less short-sighted. We just proceed. So Dijkstra's algorithm is here, and you can pause the video and study this now if you'd like. Then we also have this nice graphic that describes what is called the unit square problem. So suppose that a robot is programmed to weld joints on square metal plates. Each plate must be welded at prescribed joints on the square. To minimize the time that it takes to complete the job, the total distance that a robot's arm moves should be minimized. So we'll denote the distance between 2 points as d of p and q, and assume that before each plate can be welded, the arm must be positioned at a certain point. Given a list of points, we want to put them in order so that the distance of P0, P1 plus P1, P2 plus blah, blah, blah is as small as possible. So that type of situation is of such importance in industry that this is one of the most studied versions of the traveling salesman problem. So it is essentially the traveling salesman problem, except in that scenario, we had a robot arm that needed to move to different locations for welding, right? Okay, so what follows is the usual statement of the traveling salesman problem. So we're going to let the closed interval 0, 1 be all of the real numbers between 0 and 1. We know this from college algebra or some previous class. And then we're going to let the closed interval 0, 1 squared to be the unit square. So think of the Cartesian product of the closed interval 0, 1 with itself. So the unit square is sitting in the plane, and it's, if this is 1 and this is 1, then the unit square is just all of the ordered pairs that fall here. So given n pairs of real numbers, n ordered pairs, that represent n vertices of a complete graph on n vertices, find a circuit of the graph that minimizes the sum of the distances traveled in traversing the circuit. So this is a more typical statement of the traveling salesman problem. Since the problem calls for a circuit, it doesn't matter which vertex we start at. Assume that we'll always start at x1, y1. And I've sort of talked before about how we could always relabel these if we wanted to. Once the problem is solved, we could always change our starting position. A function can most efficiently describe a circuit in this problem. In fact, every bijection with f of 1 equals 1, every bijection from the first n natural numbers to the first n natural numbers describes a circuit. And there are n minus 1 factorial such bijections. Since a circuit and its reversal have the same associated cost, there are n minus 1 factorial divided by 2 cases to consider, because we don't need to consider going around this circuit this way and going around this circuit that way. We'll just count it once. So an examination of all these possible cases might not be feasible. Again, might not be feasible for large n. So one of the more popular algorithms for doing such a thing is the strip algorithm. And we'll go through it together. So I'm going to read through it, and then on the next slide there are graphics that I think will make it a little clearer. So first remember we're working within the unit square, and we have n points. So we're going to divide the unit square into ceiling of square root of n over 2 vertical strips of equal width, and let d be the width of each strip. If a point lies on the boundary, we're going to consider it a part of the left strip. Then starting from the left, we find the first strip that contains one of the points. Locate the starting point by selecting the first point that is encountered as you travel from bottom to top. Alternate traveling up and down the strips that contain vertices until all of the vertices have been reached, and then return to the starting point. That's phase 1. Then phase 2 will be to shift all strips d over 2 units to the right, which will create a small strip on the left, and repeat steps 1b through 1d of phase 1 with new strips. When the 2 phases are complete, choose the shorter of the 2 circuits obtained. So here are the graphs, or the visuals that I was telling you about. So let's see what it said. So first of all, how many points do we have? And it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So maybe we have about 20 points. And we take the ceiling of the number of points divided by 2, its square root. So if I have n points, I divide n by 2, I take the square root. I'm going to get most often some decimal, and then I'm just going to round up to the nearest integer. So that's how many strips in phase 1. So in this case, you can see phase 1 was 3 strips. So what we do is we locate the first dot that falls in a strip. If this strip was blank, then that would be okay. We could move to the second strip, but it's not, so we just choose the closest one to the bottom. And in the first strip, we're making our way upward. So they also said that if a point falls exactly on the dividing line, then we just count it as a part of the left strip. So the directions tell us to make our way upward like this. Then, in the next strip, we're moving down. And in the last strip, we're moving up. So this would be our path according to the directions of the algorithm. Then phase 2, if each of these strips was with D, then in phase 2, we're going to shift by D over 2 units. So this is still D, this is still D, and now we have D over 2 on this side as well. So in phase 2, we've shifted by D over 2 units, and we repeat the process. So you can sort of see what's happening as we're eliminating some of the vertices from strip 2 by pushing them, or from the first strip by pushing them over to the second strip. I'm getting a straighter course to go up. I don't have to zigzag back and forth. So each of these lines is becoming a little less zaggy or zigzaggier. Okay. And then it does go into a little bit more information here about how do you decide how to travel up and down a strip. So cases where it's not really clear which point to pick, it tells you here a little bit more information about how to choose. But we're going to see some examples of this in a little bit. So I'm going to skip through these, but just know that you can come back to this if you're trying to work on a problem and you encounter a weird situation like this. Okay, so it also comments that since the construction of a circuit consists of sorting the given points, it should come as no surprise that the strip algorithm requires a time that is roughly a multiple of n times log n when n points are to be visited. And the worst case that has been encountered with this algorithm, the circuit was obtained in square root of 2n steps. Okay, so that's about the traveling salesman problem. The other type of problem that we wanted to visit in this lecture is the maximum flow problem. In order to discuss maximum flow, we need the definition of a network. A network is a simple, weighted, directed graph that contains two distinguished vertices called the source and the sink, with the properties that the in degree of the source and the out degree of the sink are both 0. Source is connected to sink. The weight function on a network is the capacity function, which has positive weights. So think about like water flowing, since we have the word sink. It makes sense that the in degree of the source would be 0 in terms of our network. So the source just has water flowing out, and the out degree of the sink is 0 because the sink only has water flowing in. Such a graph will be called a network, or such a system. An example of a real situation would be a city's water system. Then the reservoir would be the source, while some point of distribution in the city would be the sink. The system of pumps and pipes that carries the water from the reservoir to the distribution point will make up the network. We can assume that the water that passes through a pipe in 1 minute is controlled by a pump with a maximum rate determined by the size of the pipe and the strength of the pump. The maximum rate is called its capacity, and this is the information that the weight function will contain. So here's an example of a city water system. The numbers that appear next to each pipe indicate the capacity of the pipe in thousands of gallons per minute. This map can be drawn in the form of a network. So here's the map version, and we can translate that map into a network. So source, this was the reservoir for the city, and the sink was the city. Although the material passing through the network is water, Networks can also represent the flow of other materials such as automobiles, electricity, bits of information, telephone calls, patients in a health system, and so many other things I'm sure you're quite familiar with. So that brings us to the maximum flow problem, which is derived from the objective of moving the maximum amount of water or another material from source to sink. To measure this amount, we have to define a flow. So we define a flow as a function from the set of edges to the set of real numbers, such that the flow of material through any edge is non-negative and no larger than its capacity. So in mathematical terms, that's 0 is less than or equal to the flow of material through any edge is less than or equal to the weight of the edge for all E in the set of edges. And for each vertex other than the source and the sink, the total amount of material that is directed into a vertex is equal to the total amount of material that is directed out. So in mathematical terms, that's exactly what this equation says. The sum of the flow into a vertex, so from X to V, is equal to the sum of the flow out of the vertex, so from V to Y. Then the theorem here, theorem 1.18, says that the flow of the source, the flow out of the source must equal the flow into the sink, if F is a flow. So in order to be a well-defined flow, whatever comes out of the source must flow into the sink. And that just is what it says here. The sum of the flows out of the source should be equal to the sum of the flows into the sink. The proof of that, subtract the right-hand side from the left-hand side, the result would be flow into V minus flow out of V equals 0. Now, since that's true for every V, that the flow out of V minus the flow into V is equal to 0, the result is that if we sum this up over all of the vertices except the source and the sink, all of the intermediate vertices, then the sum is still 0. So now observe that if an edge connects two vertices in this graph without the source and the sink, then its flow appears as both a positive and negative term, meaning that the only positive terms that are not canceled out are the flows into the sink. And the only negative terms that remain are the flows out of the source. So you must have that the flows out of the sink minus the flows, rather the flows into the sink minus the flows out of the source should total to 0. Okay, now the value of the flow will be that common value, that is this common value, this value. So however much flows into the sink or however much flows out of the source, the total of that is called the value of a flow, and it's often going to be denoted just by capital V of F. So we want to make sure we don't get confused because we're used to thinking of that capital V in relation to our vertex set. So it should be clear from the context which one we're talking about. Since the maximal flow consists of maximizing the amount of material passing through a network, it is equivalent to finding a flow with the largest possible value, and such a flow with the largest possible value will be called the maximal flow. So for the network in 1.16, the city water system that we saw just a moment ago, I'll just draw it here for you really quick. That was A, B, source or reservoir, and sink. And we had 20, 30, 25, 35, and 15. And then we also had these edges were labeled. This was edge 1, edge 4, edge 2, edge 5, and edge 3. Okay. So that's discussed here in this paragraph. For the network in figure 1.16, one flow, and keep in mind there could be many different flows, but one function that we could define would be F1 of E1. So that's this edge. F1 of E1 to be 25. So we're using up all 25 of the capacity for that edge. So I'm writing that as a fraction, 25 out of 25. F1 of E2 could be 20. So this is going to be 20 out of 35. F1 of E3, 0. So I'm not sending anything down that way. F1 of E4, well, if we look at what's coming down the pipes through A, there's 25. So it makes sense that this should be 25 in order to be a valid flow. And again, on this side, what's coming down the pipes through B is 20. So it makes sense that this should be 20. Then the value of the flow is going to be 25 plus 20, which is 45. But if you look at the capacity, the total capacity would be 30 plus 20, which is 50. So we can see that this flow is not too far from the solution, but we might ask the question, can we improve this flow at all? So it's not always true that the sum of the capacities, which in this case would be 50, can actually be obtained. It might not be possible due to the capacities of the previous pipes or whatever it may be in the network. The same is true for the sum of the capacities at the source. In this case, the sum of the capacities at the source is 25 plus 35, 60, which obviously can't be reached in this network because the capacity of the sink is only 50. So there's, even if I sent 60, say 1,000 gallons through this network, it has no place to go. So the best we could hope for is 50. So the solution of the maximum flow problem for this network would actually be to have a flow of 50. And what can we do? Well, we can still make the flow through E1 25. That's no problem. But then we could augment the flow through E2. We can make it 25. Now I can only send 20 down this way, so that means I need to send 5 this way. So my new flow through E3 would be 5, and that changes my flow through E4 now to the maximum of 30. So we could define the second flow instead, and then we'd have a maximal flow. Notice that this is not a unique solution. So for this problem, there are infinitely many solutions. There have been several algorithms developed to solve the maximum flow problem. And one of these is called the Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm consists of repeatedly finding paths in a network called flow augmenting paths with no improvement once the maximum flow has been attained. So what is a flow augmenting path? So given a flow F, which again we know is a function on the set of edges, given a flow F in a network, a flow augmenting path with respect to F is a simple path from the source to the sink using edges both in their forward and reverse directions, such that for each edge E in the path, the weight of the edge minus the flow through the edge is greater than 0. So that is to say, if there's room, if there's extra capacity that's unused, then we'll see if we can send more through there. And if it's used in the, that's if the edge is used in the forward direction, the flow augmenting path requires that f of E is greater than 0 if E is to be used in the reverse direction. Again, we're going to work through some examples, so it'll be become a little clearer what we mean here. So, but let's go back to the example of the city water flow. So in figure 1.16, which was source A, B, sink. So for the first function, you'll recall that we had F1 of the first edge was, so F1 of E1 was 20 out of 25. F1 of so this was 25 out of 25. So this was our initial setup, 25 out of 25, 20 out of 35, 20 out of 20, 0 out of 15, and 25 out of 30. Okay, so that was our initial flow function. So then a flow augmenting path would be exactly the one that we found. The flow augmenting path, if we were asked to find it, would be this, this, and this. And these were edges E2, E3, and E4. So the flow augmenting path is just described by the edges. But how did we know that that was a flow augmenting path? Well, we took the difference between the capacity, which is the weight function, and the flow, and we found that it was positive in all three places. On this first edge, E1, the difference between the capacity and the flow is 15, 35 minus 20. In the second edge, E2, or rather this is E2 and this is E3. In the second edge, the difference between the capacity of 15 and the flow of 0 was 15. So this should say 15. And then along this last edge, E4, the difference between the capacity of 30 and the flow of 25 was 5. So we were positive everywhere, so we knew that we could augment to this flow. The positive differences representing, of course, the unused capacity. So we could add at most 5 to find the maximal flow. So the smallest value represents the amount of flow that can be added to each edge in the path. So because we had this difference of 5, we knew that we could add 5 thousands of gallons or whatever it may be. Okay, so that brings us to our algorithm. And again, we are going to work through examples, so I'm not going to go very in depth through the algorithm, but you're welcome to pause the video now and read it for yourself. First, we define an initial flow function, f sub 0, by making the flow 0 for each edge. And then we set I equals 0. If possible, we find a flow augmenting path. If the flow augmenting path exists, then just as we just did, we determine the smallest value, like we found 5 up here above. We've found the smallest value, but there are two things. The smallest value of the difference between the weight and the flow, if it's used in the forward direction, which all of ours were, or just the flow if it's used in the reverse direction. So this reminds us that when finding a flow augmenting path, we can't actually go backwards up edges. So that's fine to go backwards up edges as long as they have strictly positive weight. So the minimum of either the difference between the weight and the flow in the forward direction or the flow in the reverse direction. And then we define our next function accordingly. So if E is not part of the flow augmenting path, then we just leave it alone. If E is used in the forward direction, then we add the minimum value that we found, this D, to that edge. Or if we're going to use that edge in the reverse direction, then we subtract it from that edge. So this is how we define our new flow function, and then we repeat this process until no new paths exist. So a couple of notes about this algorithm. It should be clear that every flow augmenting path leads to a flow of increased value and that none of the capacities in the network can be violated. Very important. Secondly, the depth first search should be used in finding the flow augmenting path since it's more efficient than the breadth first search. The depth first search will differ from the breadth first search algorithm, which we talked about in this lecture, in that you sequentially visit vertices until you reach a dead end and then you backtrack. Also, there have been networks discovered for which this Ford-Fulkerson algorithm does not terminate in a finite number of steps, but these examples have all had irrational capacities. So it has been proven that if all capacities are positive integers, as in our water flow problem, then this algorithm will terminate after a finite number of steps. So you could read the paper that was published by these researchers for more information. Also, when you use this algorithm to solve the maximum flow problem, it's convenient to label the edges of the network with these fractions as I was doing the flow divided by the weight. That just helps you keep track of where you've got extra room. Now this algorithm will be the depth first search for the flow augmenting path. So we are doing a depth first search for the sink, initiating at the source. We let E prime be the set of directed edges that can be used in producing a flow augmented path. Add a vertex to the network called start, source. Rather, add a vertex called start and an edge called start, source. So like in our example where we had source going to A or B, it's saying we're going to add one other vertex called start, and we're going to add an edge from start to source. So first, we start with S equal to the vertex set of the network, P equal to start, which was why we needed to add that vertex in. Then we move P along the edge from start to source, and we keep moving this P around. While it's not equal to start or sink, if an edge exists that takes you from P to another vertex in the set of the network, then set P to be the next vertex and delete the edge. Otherwise, reassign P to be the vertex that was reached, i.e. backtrack. If you have to backtrack back to start, then no flow augmenting path exists, else you found your flow augmenting path. So feel free to pause here and read through this in a little more detail. Here's an example, a flow augmenting path going against the flow. So we consider the network in the graphic figure 1.26 with the current flow as indicated by the labeling of the edges. So you can see these edges are labeled as fractions because this flow is, because we've already defined a flow function. So what you have is the flow divided by the weight in each fraction, or the capacity. Okay, so let's consider this network. The path, source, V2, V1, V3 sink, so that's source to V2, V2 to V1, V1 to V3, and V3 to sink, is a flow augmenting path that allows us to increase the flow by 1 unit. But you notice that we had to go backwards down the edge from V1 to V3. We had to use this edge in reverse, and we were allowed to do that because the edge had a positive flow. It had 1 unit there, so we were able to decrease it by at most 1. Then the value of the new flow that we obtain will be 8. So instead of the values that we see here, we're going to have 5 out of 5, because we added 1, 1 out of 2, then this is 0 out of 3. We subtracted that 1. And then this is going to be 4 out of 5. Okay, so the new flow is 8, and this flow must be maximal since 8 is the most that we could send out of the source. So this maximal flow is going to be defined here, just as I relabeled the vertices and the edges, rather, on the other graph. 5 out of 5, 1 out of 2, 0 out of 3, and 4 out of 5. Okay, so there are just a few other graph optimization problems that we might want to consider. One that we'll probably see coming up in this class is the minimum spanning tree problem. So given a weighted graph, find a subset of the edge set with the properties that the graph made by the vertices and the new edge set, the subset, is connected, and the sum of all the weights of the edges in the subset E prime are as small as possible. So this will be in your module on trees. Also of interest is the minimum matching problem. Given an undirected weighted graph with an even number of vertices, pair up the vertices so that each pair is connected by an edge and the sum of these edges is as small as possible. A unit square version of this problem also exists and has been studied extensively. So we might not get to that in this course, but this is something cool that you can look up and read about. Also, the graph center problem, given a connected, undirected, weighted graph, find a vertex, which you'll call the center in the graph, with the property that the distance from the center to every other vertex is as small as possible. As small as possible could be interpreted as either minimizing the sum of the distances to each vertex or as minimizing the maximum distance from the center to a vertex. So this is just a preview of other types of graph optimization problems that are really fun and interesting, but for now we're just going to stick with the traveling salesman problem and the maximum flow problem. We do have exercises for this section, but I want to pause this video here so that it doesn't get too long, and we'll do the exercises in a separate video.